In this video, I'll show you how AFR works, not as a concept, but in motion, and why it is structured the way it is. Hi, I'm 𝗲𝘂𝘁𝗁𝗏. In this video, I'll walk you through AFR, a local-first, auditable retrieval system, and explain why it exists, how it's designed, and what kind of AI automation work it represents. Let's start from the system itself. When people start experimenting with AI over documents, the focus is usually on how quickly an answer can be generated. What often receives less attention is what happens after the answer is produced. Questions like, where did this answer come from? Which documents were actually used? What happens when the documents change? And how would you explain the results to someone else later? AFR was built to explore those questions. Not how to make AI respond faster, but how to make it respond in a way that is understandable, inspectable, and safe to rely on. So, what is AFR? AFR stands for Automated File Retriever. At a high level, it's a system that takes a collection of documents from a designated watch folder on your computer and makes that content queryable through natural language. What I was interested in while building it was not just whether an answer could be generated, but whether the path from documents to answer could be clearly understood and inspected. AFR is structured as a set of workflows that handle document ingestion, retrieval, answer generation, and validation as a separate concern, so each part can be reasoned about independently. The question I was trying to explore with AFR is this: how can people ask natural language questions over internal documents while still understanding and trusting how the answers are produced? To make that possible, a few design principles had to be decided up front. While building AFR, I tried to be deliberate about a few design choices that kept coming up as important. One of them was keeping everything local by default. The documents live on the same machine and the system works within that boundary. That made it easier to reason about where the data goes and who and what has access to it. Another was ensuring that answers remain tied to the actual source content. If the system can't find enough supporting material in the documents, it shouldn't try to fill in the gaps. It should be clear when an answer is based on evidence and when it isn't. I also paid close attention to separating responsibilities within the system. Ingestion, retrieval, answer generation, delivery, and validation are handled independently, so changes in one area don't quietly affect everything else. And finally, I wanted the system to be observable while it runs. Not just whether it succeeds or fails, but what it actually does at each step, so the behavior can be inspected later if needed. Those principles shape how the system is structured in practice. Let me walk you through how the system is structured, not at the level of individual nodes, but in terms of responsibilities. AFR ingestion handles the documents themselves. It reads files from the watch folder, extracts their content, breaks it into chunks, and keeps track of changes like updates or removals. AFR RAG Core is where retrieval and answer generation take place. Relevant content is selected, assembled into bounded context, and used to produce answers that can be traced back to the source documents. AFR chat entry is responsible for how questions enter the system. Using a single entry path keeps behavior consistent across interactions. AFR global error handling captures execution failures so they can be reviewed later. And AFR 𝗂𝗄𝑎𝑐𝗺 is used to validate that the system continues to behave as expected as it evolves. Now that the overall structure is clear, I want to spend a bit of time on the ingestion side of the system, because this is where most of the long-term reliability decisions are made. The first thing AFR does is treat the file system itself as the source of truth. Instead of reacting to individual events, it periodically looks at the current state of the watch folder and compares it to what the system already knows. The question this part answers is simple. What exists on disk right now, and how does that differ from the last known state? From that comparison, files are classified as new, changed, unchanged, or deleted. That classification drives everything that happens next, so this step is about establishing a clean baseline before any processing begins. Before any file is parsed or processed, AFR makes sure it can actually be read safely. This part answers a very practical question. Can this file be opened and read without errors? File system level issues like permissions, missing files, or encoding problems are handled here before they can affect the rest of the pipeline. If a file can be read, it's logged explicitly and excluded from further processing. That way, downstream logic only ever operates on inputs that are known to be valid. Once a file is confirmed readable, AFR routes it through a parser based on its type. PDFs, Word documents, spreadsheets, and plain text files each follow their own extraction path, but the focus is always on extracting text that already exists in the file. AFR does not attempt to interpret images or perform optical character recognition. If a document contains only images of text, that content is intentionally ignored. The question this part answers is, how do we turn existing text content from different file formats into a consistent, system-safe representation? Regardless of where the text comes from, the output is normalized into a common internal structure with provenance preserved so every extracted segment can be traced back to its source. Ingestion isn't only about adding new information, it's also about removing what no longer belongs. This part of the workflow handles deletions and updates explicitly. The question it answers is, how do we make sure the database reflects what actually exists on disk and nothing more? When files are removed or changed, their previous representations are cleaned up before anything new is written. This prevents stale content from lingering in the system and keeps the knowledge base aligned with reality over time. Once content has been safely extracted and normalized, it's ready to become searchable knowledge. Here, documents are split into chunks, embeddings are generated, and everything is stored with clear links back to the original file and location. The question this step answers is, how does raw document content become retrievable knowledge without losing traceability? This is the point where files stop being files and start functioning as a structured knowledge source that the rest of the system can reason over. When you look at the ingestion workflow as a whole, what matters isn't any single node, but the order of decisions. State is established first, safety is checked before parsing happens before normalization, cleanup happens before new knowledge is written. The entire workflow is designed so that each step answers a specific question before allowing the system to move forward. Once documents have been ingested and turned into structured text-based knowledge, the next question is how that knowledge is actually used to answer questions. That's what AFR RAG Core is responsible for. The first step in the RAG workflow is making sure the user's question is in a form the system can reason about consistently. The question this grouping answers is, how do we turn a free-form user question into a deterministic retrieval-ready query? Here, the raw input is normalized, defaults and guardrails are applied, and structured query object is produced. This creates a clean boundary between how a question is phrased and how retrieval logic operates, so downstream behavior stays predictable and repeatable. Once the query is prepared, AFR needs to decide which pieces of knowledge are actually relevant. The question here is, which chunks are legitimate evidence for this question and in what priority order? Instead of relying on a single retrieval method, AFR combines semantic similarity with lexical matching. This helps balance conceptual relevance with exact wording and produces a strict ordered list of candidate evidence chunks that the rest of the system can reason about explicitly. The next step is to transform the ranked retrieval output into a strictly bounded context window with explicit citation anchors, ensuring downstream reasoning remains grounded and traceable. The question this part answers is, what evidence is safe to show to the model and how is it grounded? Here, the top-ranked chunks are assembled into bounded context window with stable citation references attached to each segment. This step also makes an explicit go or no-go decision about whether enough evidence exists to proceed, which prevents the model from reasoning beyond what the system can support. Once a validated bounded context is available, the system can generate an answer. The question here is, given this context, how is the raw natural language answer generated and which execution path is used? AFR uses a local-first approach by default, with an explicit option to route generation to a cloud model when configured. Regardless of which model is used, generation is constrained to the provided context, with the fallback behavior defined when evidence is insufficient. The goal is that answers may vary in wording, but not in what they claim to be true. Generating an answer is not the final step. The system also needs to deliver it in a controlled, inspectable way. This part answers the question: how should the system safely deliver and persist the final answer, and how do we prove it later? Here, the raw model output is normalized into a consistent response structure, and the result is walked along with the execution metadata. In AFR, an answer isn't considered complete until it has been formatted, validated, and persisted as a traceable result. When you look at RAG Core as a whole, it's less about generating text and more about managing decisions. Questions are normalized before retrieval, evidence is ranked before it's assembled, context is bounded before generation, and answers are finalized before they are delivered. Each step exists to answer a specific question, and each boundary makes the system easier to reason about when something needs to be inspected or changed. At this point, it's worth addressing a reasonable question. Much of what AFR does could be implemented using a single AI agent. And in fact, I built both local and cloud-based agents against the same knowledge base. Those agents can retrieve documents and generate answers just fine. The difference isn't capability, it's responsibility. An agent decides how to act internally. AFR makes those decisions explicit, inspectable, and enforceable at the system level. AFR exists for the moment when the agent answered is no longer a sufficient explanation. So far, I've shown how documents are ingested and how answers are constructed. The remaining piece is how questions actually enter the system and how answers make their way back to the user. That's what AFR chat entry handles. AFR can accept questions from more than one place. For example, a chat interface or a webhook used for testing and QA. The first thing this workflow does is normalize those different entry points into a single shared input format. The question this grouping answers is: how do we make sure every question enters the system in a consistent, predictable way? By establishing one canonical input contract, the rest of the system doesn't need to know where a question comes from, only that it meets the expected structure. Once the input is normalized, AFR chat entry invokes the RAG Core workflow as a separate service. The question here is: how do we trigger retrieval and answer generation without coupling it to the user interface? The RAG Core runs independently, produces its result, and returns structured output that can then be shaped for delivery. This separation keeps reasoning logic isolated from presentation concerns and makes it easier to evolve each part without unexpected side effects. After an answer is produced, the system still needs to decide how it should be delivered. This part of the workflow answers the question: where should this response go, and how do we record that it was delivered? Responses can be routed to different destinations, such as chat UI or QA path, while delivery events are logged explicitly. That way, the system doesn't just generate an answer, it also keeps evidence that the answer was actually sent. When you look at AFR chat entry as a whole, its role is mostly about boundaries. Entry points are unified before processing, reasoning is delegated, not embedded, and delivery is handled explicitly rather than implicitly. This keeps the chat layer thin on purpose, predictable and interchangeable, without letting UI concerns leak into the core of the system. Up to this point, everything you've seen in AFR focuses on producing answers in a controlled and explainable way. AFR QA suite exists for a different reason. It's there to continuously check whether the system behaves the way it claims to behave, not by asking for opinions, but by running the system itself under controlled conditions and inspecting what actually happens. Every QA run starts the same way. A test run is initialized, the context is defined, and test scenarios are expanded into concrete work items. Nothing runs implicitly. Each test case is explicit, named, and routed by intent, whether it targets ingestion, retrieval, or chat behavior. This makes QA deliberate rather than ad hoc. You can always see what is being tested and why. When a test runs, the QA suite does not simulate behavior. It executes the actual AFR workflows, ingestion, RAG Core, or chat entry, as they are used in production. Barriers and weights are intentional. They make execution order explicit and isolate each step so that timing or overlap doesn't hide problems. In this setup, the QA suite acts as a supervisor, not a participant. It observes the system, but it doesn't interfere with how the system works. After execution, the focus shifts from "did something run" to "what state did it leave behind?" The QA suite inspects database rows, stored artifacts, vectors, logs, and metadata, the same things AFR itself relies on. These raw states are normalized into assertion-friendly shapes and checked against explicit expectations. At this stage, the system is not judging answer quality or usefulness, it is verifying guarantees: what should exist, what should not, and whether the system respects its own rules. When something fails, the goal here is not to recover silently or push forward. Failures are first captured and logged with their context, so there is clear evidence of what went wrong and why. Once a failure is confirmed, it is treated as a blocking condition. The run is explicitly stopped, and the error is surfaced as part of the QA result. This makes the outcome unambiguous. A failed guarantee cannot be ignored, and it cannot quietly pass downstream. The QA summary is only produced when all checks have passed. At that point, results from the different QA branches are merged, a final verdict is assembled, and the supporting evidence is written to the system logs. This summary represents a confirmed state. The system behaved exactly as expected for the scenarios under test. If a failure occurs earlier, this step is never reached, which is intentional. The absence of a summary is itself a signal that something needs to be fixed before the system can be considered valid again. AFR QA suite doesn't try to prove that answers are good. It focuses on something more basic and more fundamental: whether the system behaves consistently, predictably, and according to its own design. When expectations are violated, the run stops and surfaces that failure immediately. When everything passes, the system produces a clear, auditable confirmation that its guarantee is held, and when they don't, the system refuses to pretend otherwise. That covers failures we expect and deliberately test for, but not every error in a system is planned, and that's where the global error handler comes in. The global error handler exists to catch anything that escapes normal control flow: unexpected crashes, unhandled exceptions, or failures that occur outside the QA paths. When an error is triggered, the handler captures a minimal but sufficient snapshot of what happened, which workflow was running, which node failed, and the error message itself. That information is written to a dedicated error log, separate from the normal execution and QA results. This mechanism can also be used to trigger alerts to external systems or monitoring tools. At the moment, it is intentionally configured only to persist errors in the database, keeping the behavior simple and observable. The goal here is visibility, making sure system-level failures are recorded clearly, even when they weren't anticipated. Once unexpected errors are handled, the next question is broader. What does the system record about itself while it runs? Observability in AFR is not limited to one workflow. From ingestion to knowledge construction, to retrieval, to chat delivery, the system keeps track of what it's doing. Events are logged as they happen, and they are linked across workflows. So you're not just looking at isolated outputs. You can follow how something was processed, selected, and eventually returned. For example, when a question is asked, the system records what was asked, what evidence was retrieved, and what response was delivered. But that is just one layer. The point is that the behavior across the system can be reviewed later, not reconstructed from memory. It is simply about being able to see what actually happened. Generating an answer usually isn't the hardest part. The harder part is understanding what the system actually did. Why did it give that answer? What is it used to produce it? And what happens when something changes? That's what I tried to design for with AFR. Not just answers, but behavior you can follow, inspect, and make sense of later. This is not meant as a pitch. It's just how I think about building AI systems. For me, features matter, but so does thinking about what can go wrong. I try to keep responsibilities separate, and I want to be able to see what the system actually did, not just what it returned. Models can change, agents can change, I'll keep using them. What matters is how they fit into the system around them. If this approach makes sense to you, feel free to connect. I will keep building systems like this. Thanks for watching. Till next time.